This is week 19, page 2, number 5. Page 2, number 5. Formic acid is a weak monoprotic acid that is partly responsible for the irritation of insect bites. If the initial concentration of formic acid is 0.100 molar and the equilibrium concentration of hydronium is 0.0042 molar, calculate the acid dissociation constant. As usual, the first thing we do is write an equation. In order to write this equation, we need to know what the molecular formula for formic acid is. So we look in the book on one of the charts in the book, and it tells us that the formula is HCO2H. We have to add water because we know that the acid is added to water to make an aqueous solution. When formic acid donates a proton or a hydrogen ion to water, it becomes hydronium. We see that there are now 3 H's because one of the hydrogen protons was added to water. So that gives us H3O, which is called hydronium. It has a positive charge because the hydrogen that was added is a proton. The electron was not added to the water. In this particular equation, the water, since it is accepting a proton or accepting a hydrogen ion, the water is acting as a base. We remember, according to the textbook, or from the textbook, that water can act as either a base or an acid. Now we see that we have CO2H that's left after the hydrogen proton was donated to water. This particular compound has now got a negative charge because when a proton is given away and the electron is kept in this particular molecule, the electron doesn't have a positive charge to balance it out, so the whole molecule has a charge of -1. We see that this equation has both a forward and a reverse arrow, and that's because formic acid is a weak acid. We know that a weak acid does not go to completion, and therefore we show both the forward and the reverse reactions. Now the problem tells us the concentration of the formic acid at the beginning of the, when it was first added to the water, and that's 0.100 molar. It also tells us the concentration of the hydronium when the reaction reaches equilibrium. Since we know the initial concentration of formic acid, which is 0.100 molar, we can tell what the concentration of formic acid is after it has dissociated in the water by subtracting the concentration of one of the 2 ions that are produced by the dissociation of formic acid. You see here I've written the initial concentrations of everything except the water. We don't write the water because the water remains constant. So since it doesn't change, it doesn't affect our numbers. We're only looking for what changes. So when formic acid is poured into the water, its concentration is 0.100 molar. And at the very beginning of when the formic acid is poured into the water, there are no hydronium ions and there are no formic acid conjugate bases. Now, as this reaction proceeds, some of this formic acid is broken down into hydronium and the conjugate base. Therefore, the amount of formic acid as a whole unit in the water has decreased. We can tell how much it has decreased by subtracting the concentration of hydronium. So we see that after the formic acid dissociates, it has given up 0.0042 molars of concentration of itself, and it has dissociated that much. The amount that's left is 0.0958 molars. Now, at the beginning of the reaction here, there were no hydroniums, we said, and there were no conjugate bases of the formic acid. As the reaction proceeds, though, it tells us when it gets to equilibrium that the concentration of each of the hydronium is 0.042. I'm sorry, 0.0042. Since one of these molecules breaks down to one of these and one of these, we know that the concentration of each of those is going to be the same. And since the concentration over here is increasing as the reaction proceeds to equilibrium, we're going to add the concentration here to what the initial concentration was, which was 0. Now we know what the concentration of each part of this reaction is at equilibrium. The next thing we have to do is write the acid dissociation constant expression. I started out by writing the equilibrium constant expression, which has the concentrations of the two products on the top of the fraction and the concentrations of the two reactants on the bottom of the fraction. Now, in order to get an acid dissociation constant, we have to realize that the amount of water in the reaction is a constant itself. And anything that's a constant has to be on the side of the equation that is the constant side. Therefore, we have to get rid of water on this side of the equation. So what we do in order to get rid of water on the bottom of the fraction is we multiply both sides of the equation by water. Of course, water cancels itself out here. And water is incorporated into the equilibrium constant on this side, and we change the name because it's not exactly the same as the equilibrium constant when we add the constant amount of water in. And now we're going to call it the acid dissociation. Now we're going to replace what's left in this constant with the numbers for concentrations that we already found. So we replaced the concentration of hydronium and the concentration of the conjugate base of formic acid with 0.0042. We replaced the concentration of formic acid with 0.0958 molarity. We do the math and it comes out to 0.00018, and we're going to change this number to be using scientific notation by moving the decimal point 3 places to the right. Actually, that was 4 places to the right. When we move to the right, we subtract exponents, so we have 1.8 times 10 to the negative 4th as our answer for what is the acid dissociation constant. This is week 19, page 2, number 7. This is week 19, page 2, number 7. Acetic acid is the conjugate acid of the acetate ion. It is a weak monoprotic acid that dissociates to an acetate ion and a hydronium ion in aqueous solution. Calculate the acid dissociation constant for acetic acid if a 1 molar solution results in an equilibrium of hydronium concentration of 0.0042 molar. The first thing we have to do is write the equation. Here we have the equation for the reverse reaction of acetic acid in water, which dissociates to form hydronium ions and acetate ions. Notice that the arrows are going two ways, which tells us, or is because, acetic acid is a weak acid and it will not go to completion. The reaction will not go to completion. The question is asking us to find the acid dissociation constant. So before we can do that, we need to find the concentration of everything here except the water. Since the water, the first thing I write down is the initial concentrations of each of these substances: the acetic acid, the hydronium, and the acetate ions. The next thing I'm going to do is I'm going to subtract from here the concentration of hydronium ions that was given to us in the problem. And that's because as the acetic acid breaks down or dissociates in solution, some of it breaks apart and becomes hydronium and acetate ions. So whatever the concentration of one of these is can be subtracted from the initial concentration to find out the concentration at equilibrium. So we subtract the concentration of hydronium ions from the initial concentration of acetic acid, and we get 0.9958 molar. Since the hydronium and the acetate ions start out with a concentration of 0 and they're increasing in concentration, we add, because adding increases an amount. We're going to add the amount of the concentration at equilibrium, and they're both the same because there's one of each of these for every molecule of acetic acid that dissociates in water. Now the next step is to write the acid dissociation constant expression. The acid dissociation constant has already included in it the concentration of water, so we don't have to put water in as part of the expression. We have the concentrations of the two products, hydronium and acetate ions, and we have the concentration of the reactant on the bottom. Now we're going to replace these with numbers. So we replace the concentrations with numbers. We do the math. It comes out to 0.0000177. Since there are only two significant digits in these, we're going to round that to 1/8 and change it to scientific notation. And we get 1.8 times 10 to the -5th for the acid dissociation constant. This is week 19, page 3, number 8. Apparently, I copied this wrong from the teacher's manual. So I'm going to have you take a few minutes to just change the problem on your paper so that it reads, ammonia is a weak base. The initial concentration of ammonia is 0.150 molar, and the equilibrium concentration of hydroxide is 1.6 times 10 to the -3rd molar. Calculate the base dissociation constant for ammonia. Now, of course, the first thing we're going to do is write an equation. In this equation, we see that ammonia is actually a gas, which is added to the water, which is a liquid. It results in an ammonium ion with a positive charge and a hydroxide ion with a negative charge. Again, we have initial concentrations of the gas that's added to the water. We have concentration at equilibrium of the hydroxide ion. So we're going to start by writing down the initial concentrations of ammonia and each of the ions. So here's the initial concentration of ammonia, 0.1500 molar. We know that as it dissociates, it will become smaller, so we're going to subtract the concentration of hydroxide that's been given to us. We get 0.1484 molar of ammonia at equilibrium. We get 0.0016 molar of the ammonium ion at equilibrium, which is of course the same as the concentration of the hydroxide ion at equilibrium. Next, we have to write the base dissociation constant, which is essentially the same thing as the acid concentration, which is essentially the same thing as the acid dissociation constant. So we have on the top of the fraction the ammonium ion, the hydroxide ion. On the bottom of the fraction we have the reactant from the left-hand side of the equation, ammonia. Water is not included here because water has been brought over to the constant side and included in the base dissociation constant. Now we're going to replace these with numbers. The concentrations with the numbers for the concentration in molarity. We get 0.000017. Change that to scientific notation. 1.7 times 10 to the negative fifth is the base dissociation constant for ammonia. This is week 9, homework sheet, page 3, number 9. A 2.00 molar solution of a weak acid has a hydrogen ion concentration of 9.86 times 10 to the negative fifth molar. What is the value of the acid dissociation constant for this acid? So now we have an acid that we don't know the name of, but we can still write an equation representing this acid and the results of its dissociation. So here we have a basic equation for the dissociation of an acid. We have HA, which represents the acid. H represents the hydrogen ion or proton, that will be donated as part of the acid dissociation. We have water that it's dissolved in. We know that that hydrogen ion will bind with a water to create a hydronium ion. We know that the acid, when it loses the proton as a hydrogen ion, will now have a negative charge, and it will no longer have the hydrogen with it, and it will now be the conjugate base of that particular acid. Now we're going to write down the initial concentrations of each thing that has been given to us. So the problem told us that the initial concentration of this particular acid was 2 molar. I put a whole bunch of zeros here so that it would be easier to show the subtraction. We're going to subtract the concentration of hydrogen ions, which is going to be the same as the concentration of hydronium, because each hydrogen attaches to one water to make a hydronium. Over here we had an initial concentration of 0 for the hydronium and the conjugate base of this particular acid. We know that the concentration of hydronium is this, therefore the concentration of the conjugate base ion will also be this. Now we get a concentration of 1.9999014 molarity for the acid. The concentration for these is the same. Next, we write the acid dissociation constant expression, which shows the hydronium and the conjugate base from the right-hand side of the equation, or the products on the top of the fraction, and it shows the reactant or the acid on the bottom of the fraction. We replace it with numbers, and it comes out to 4.86 times 10 to the negative 9th. And that is the acid dissociation constant for this particular acid. This is just a hint for problem number 12 on page 3 of week 19's homework. This is not an online problem, but I do want you to realize that they've given you the number of moles of pyridine and the number of milliliters of water. They have not given you the molarity. You have to find the molarity yourself of the initial concentration before you can solve the problem. This is week 19, page 4, number 14A. It says, answer the following questions in relation to the reactions 1 and 2. Notice that, again, I made a mistake on this homework sheet, and reaction 2 should not have an H here by the phosphate ion, and it should be H3O, a hydronium ion, not water, with a 2. So please just change that on your homework sheet so that you'll be able to follow along. So question A says, identify the conjugate acid-base pairs in both reactions. So let's look at reaction number 1. We have phosphate ion, which is a base. It's negative, so it can attract or accept a hydrogen ion, which is positive. We have water, in which the reaction occurs. It yields phosphoric acid and hydroxide ions. Notice that the phosphoric acid has a H in front of it because it has accepted a hydrogen ion from water, and it now has a charge of -2 rather than -3 because that one positive proton that was added to it canceled out one of those negative charges. Notice that the water has lost a positive charge and a hydrogen ion, and it therefore is now a hydroxide ion with a negative charge. This phosphate ion is a base because it can accept a hydrogen proton. Here we see that it did accept the hydrogen proton. Now, on this side of the equation, this phosphate ion has become an acid because now that it has a hydrogen proton, it is able to donate or give away that hydrogen proton, which is a characteristic of an acid. So we see that the base becomes an acid when it does its job of accepting a hydrogen ion, and the acid, the conjugate acid of that base, now is able to go in the reverse direction and give back a hydrogen ion so that water will be water and it will turn back into phosphate ion, which is a base. So this is the conjugate base and this is the conjugate acid. Here we have phosphoric acid plus water yields a phosphate ion and a hydronium. This acid here, by definition, is able to give away a hydrogen ion. We see that it does that. It gives the hydrogen ion to the water, which causes the water to become a hydronium ion. And when it has given away the hydrogen, it becomes a phosphate ion without the hydrogen. It now has a larger negative charge because it lost a positive. And when you lose a positive, you gain a negative. Well, you don't gain a negative, but the ion becomes more negative. Now this is an acid, but this is able now to accept a hydrogen ion, and therefore it's a base. So this would be the conjugate acid, phosphoric acid, and this particular ion, phosphate ion, is its conjugate base. Notice that an acid turns into a base when it does its job of giving away a hydrogen ion, and the base turns into an acid when it accepts a hydrogen ion. Week 19, page 4, number 14b says, what property of water do reactions 1 and 2 demonstrate? Well, we see in reaction 1 that hydrogen is donated by water or given away by water. And so anything that is able to donate a hydrogen ion is technically an acid. So when the hydrogen from the water is given to the phosphate, water is acting as an acid. But in equation number 2, the water accepts a hydrogen ion from the phosphoric acid and becomes hydronium. So here the water is acting as a base because it's accepting a hydrogen ion. The property of water that this exemplifies is the fact that it is amphoteric. Which means it can act as either an acid or a base. Week 19, page 4, number 14c says, write the equation for a reaction in which phosphoric acid acts as a base and water acts as an acid. So we'll start with phosphoric acid. So I've started with phosphoric acid, and I add it to water because we know this is going to happen in solution. Now, in order for phosphoric acid to act as a base, it has to be able to accept another hydrogen ion. So, as a result, the phosphoric acid would have not one hydrogen here, but 2. We put a 2 here by the hydrogen to show that it has accepted another hydrogen proton. The proton has a positive charge, therefore the charge on this particular molecule goes from -2 to a -1 because the positive charge of the hydrogen cancels out one of the negatives. Now, water acted as an acid, meaning that it donated the hydrogen ion to this to make it into H2PO4. Therefore, water now has one less hydrogen. When we take a hydrogen away from water, we get a hydroxide ion. The electron stays with the water, only the proton is donated. Therefore, we have a negative charge on the hydroxide. And that is the equation. This is week 19, page 4, number 15. Write the chemical equation for the reaction of methylamine and nitric acid in water. Is the product solution slightly acidic, slightly basic, or neutral? Explain. So in order to write this equation, we are going to start with the methylamine. Notice the methylamine is a base. And we know that methylamine is a weak base because in the book it tells us that it's a weak base. We're adding it to an acid. The acid we're adding it to is nitric acid, which, according to the book, is a strong acid. Now, when we add an acid and a base together, what do we get? Well, we get a salt. In this case, what's happening is we're adding the acid and the base together. This hydrogen here comes and it combines with the base, methylamine. Now notice that when I added this hydrogen to the methylamine, I added it to the NH bond and not to the CH bond. Now that's because nitrogen and hydrogen create a polar covalent bond. They have a large difference in electronegativity, whereas hydrogen and carbon do not have a large difference in electronegativity, and there is no polarity here. When a hydrogen ion or hydrogen is added to another molecule, Since it has a positive charge, it's going to go to a place where there is a polar configuration. And we know that nitrogen and hydrogen bonded together have a polarity. We also know that nitrogen always bonds with an unshared pair of electrons. Here we show nitrogen, and it's capable of sharing 3 electrons, and then it has 1 unshared pair, which creates a bit of a negative charge there at the top of the nitrogen. And that negative charge attracts that hydrogen ion. So as a result, we have a salt here that we know is going to be slightly acidic because we had a strong acid that was added to a weak base. And the book told us the different combinations. And when a strong acid is added to a weak base, we get a slightly acidic salt.